All right, let's look at nomenclature of acids. All right, in order to name acids, we have to be able to recognize them, and there are two principal types of acids. One is binary acids, and so we'll look at those, and the other are oxyacids. Now, binary acids are simple. The prefix bi, of course, means two, and so binary acids are those that are composed of two elements, a hydrogen and a non-metal anion. Right? So these would be things like hydrogen and chlorine, which would give you hydrochloric acid, or hydrogen and bromine, which would give you hydrobromic acid. But when we say binary in this case, binary means two elements. It doesn't necessarily mean two atoms. So for example, you can also have a binary acid with sulfur, and because sulfur is two steps away from argon, when it forms an anion, it forms a 2- anion, and so in order to neutralize that 2- charge, you need two hydrogens. So the binary acid with sulfur would be H2S, which is hydrogen sulfide. All right, let's look at naming these, because there's a little bit of a trick to binary acids. All right, binary acids can exist in two different forms. They can exist as gases, and all of these gases are very water soluble, so you can dissolve them in water to make solutions. And what's important about these is that the name of the compound is different depending upon whether it's in the gas phase or as a solution. So in the gas phase, each of these is named, it's a covalent compound, but it's named as if it were an ionic compound. So the binary acid between hydrogen and chlorine, like this, we would follow this pattern here. The name is hydrogen blank ide, and then you just put in the root for the acid in there. So when HCl is a gas, it's a covalent compound, which we would name hydrogen chloride. Right? And the same thing would be true for the other halogens, hydrogen fluoride, hydrogen bromide, hydrogen iodide. And as we mentioned a little bit ago, because sulfur forms a 2- ion, the form of this one is H2S. So this would be hydrogen sulfide. Right. All right, now all of these, as I mentioned a minute ago, these are all very soluble covalent compounds. You can dissolve them in water, and when you dissolve them in water, they make acidic solutions. And the acidic solutions formed from them are named, with this pattern, hydroiodic acid, where the root for the element goes into that little blank. So just as we had HCl in the gas phase as hydrogen chloride, HCl dissolved in water is an acid, which we would call hydrochloric acid. Right? And likewise, we had this example on the last one. As a gas, H2S is hydrogen sulfide, but as a solution, it is hydrosulfuric acid. All right. Now these are These are made from the anions, simple anions on the right-hand side of the table, the nonmetals. But really, it's almost only the halogens and sulfur, of course, as we just did an example. And the reason is, if you look at the periodic table over there on the right-hand side, right? These guys over here, the halogens, they all form binary acids: hydrofluoric acid, hydrochloric acid, hydrobromic acid, right? And sulfur, we did that one as an example, hydrogen sulfide and hydrosulfuric acid. Selenium also does that, right? So we can have hydroselenic acid and hydrogen selenide, right? But these guys over here, if you do this with oxygen, you get H2O, which in a sense can be considered an acid, right? But as far as nomenclature is concerned, that's water, right? So we don't need to worry about nomenclature rules for that one. Same thing is true with this one. If we put hydrogens on nitrogen, we get NH3, which is ammonia, right? So we don't need to worry about that one, right? Same thing is true of pH3. We haven't talked about this, and you don't need to memorize it, but pH3 is called phosphine, right? So that one also would not be considered an acid. So really, for these binary acids, it really is just the halogens and sulfur and selenium. It's just those 6 different elements that we're concerned with here. All right, the other group are oxyacids, and whereas the binary acids are simple anions combined with enough hydrogen to balance out the negative charge, the oxyacids are the same thing, but using those oxyanions, right? So if you have an oxyanion and you add enough hydrogens to make a neutral compound, then that gives you an acid. So for example, one of our oxyanions was the nitrate ion, right? This has a -1 charge, so to balance that negative charge, we would need 1 hydrogen. So if we add 1 hydrogen to that, we get nitric acid, right? We've also got carbonate ion. Right? In this case, we're looking just at these ones that end with 8. Carbonate has a 2- charge, so in order to neutralize that, we would need 2 hydrogens. So the corresponding acid would look like this, and this would be carbonic acid. And you can see how that name works. If you take the oxyanion that ends with 8, convert it to an acid, and then the name becomes whatever the root is, and then ic acid. So for example, see if you can figure this one out. PO4 3- is phosphate ion. So if that ends in 8, go ahead and write the formula and the name of the corresponding acid. All right, since that has a -3 charge, we would need 3 hydrogens. So the formula of the acid would be H3PO4, and then the name would fit the same pattern. Phosphoric acid. Now, just as we had with the, we're looking at the oxyanions themselves, we could change the number of oxygens, like we could have chlorate and chlorite and perchlorate and hypochlorite. The same thing is true of the oxyacids. And so we're going to look at how those names vary as we change the number of oxygens. All right, so we're going to set up a table just like we did before with the different forms of these oxyanions. And the first thing to note is, as we had on that last page, if the oxyanion ends in 8, then the corresponding acid ends with ic acid. And as we were showing last time, you can add an extra oxygen to that to get the perchlorate ion. Right? Notice the number of oxygens has gone up by 1, but the charge stays the same. So if we take that perchlorate ion and form the corresponding acid, the name for the acid is now perchloric acid. Right? And you can see there's a parallel here in the name of the oxyanion. We added the prefix per, and in the name of the corresponding acid, we also added the prefix per. Right? So there's a parallel there. And as we did before, we can reduce the number of oxygens by 1 to go from ClO3 to ClO2. And when we do that, of course, we get chlorite. So now our suffix changes. And for the corresponding acid, the suffix here also changes. So we go from chloric acid to chlorous acid. And you can probably guess what will happen if we remove one more oxygen to go to ClO. Remember that that changes the name of the anion from chlorite to hypochlorite. Right. So we add this prefix here. And then for the corresponding acid, this same prefix again. Right. So these two things are almost exactly parallel, right? The only difference is that for the names of the anions, 8 goes to ic, and ite goes to us, right? But the prefixes up here and down here are the same for both the anions and the corresponding acids. Okay. All right, so let's try one of these. We had on the last page NO3, which we said was nitric acid, right? And that's because NO3 is nitrate. So if we go down one, in fact, I'm going to go ahead and write the, give me a second, I'm going to write the name of the ion in here also. So if we remove one oxygen, NO2, this gives us the nitrite ion, and the corresponding acid, I should have written the formula over here, HNO3, the corresponding acid is nitrous acid, and the formula is HNO2. And that same pattern is followed for sulfuric acid and sulfurous acid, phosphoric acid and phosphorus acid, and so on and so forth. Not all of them have all 4 different forms here. For example, there is no percarbonic acid, right? Carbon just doesn't form that particular compound. But to the extent that you can form those by adding and subtracting oxygens, this pattern is followed for the nomenclature. Okay, so let's try some practice. go ahead and write names for these guys. Hit the pause button, write names for these, and then unpause it, and we'll see if we get the same results. All right, for the first one, we've got HF, and this is just two elements. So it's a binary acid. And for a binary acid, we have to be concerned with the state. Remember, the gases and the aqueous solutions are named differently. Since this is in the gas phase, we name it following the rules as if, kind of as if it was an ionic compound, right? So we call this hydrogen fluoride. And then here we have the same compound, but now it's in solution. So we use the other naming system, naming this as an acid. And so we'd call this hydrofluoric acid. Right. Now, H3PO4, we should recognize that as an oxyacid. And to name the oxyacids, we have to remember what the 8 form is. And so if PO4, 3 minus, is phosphate, right? This has the same number of oxygens here. So that means if we make that into the corresponding acid, I wrote phos twice. What am I doing? So if we make that into the corresponding acid, that will be phosphoric acid. All right. Now here is another oxy acid. We have to remember the 8 form. That's the important one for all of these. And the 8 form is SO4, 2 minus, which is sulfate. Right. So here we see that we've lost one oxygen. So that means we've gone from the sulfate ion down to the sulfite ion. And when we make the corresponding acid from one of these that has one fewer oxygens, then the name of the acid, instead of ic, the name of the acid ends in us. So this would be sulfurous acid. All right, and the last one here, HBrO4, again, that's an oxyacid. So we need to think about the 8 form for the bromine oxyanion. The 8 form is BrO3. So we can see that we've added one oxygen, so we're going up one step in that table that we had before. And if we go up one step in the table, then, oops, 4. If we go up one step of the table, then we keep the same suffix, ic, but we add the prefix per. So this is perbromic acid. All right. Lovely. All right, one more page of practice problems. We'll go the other direction. All right, so now take the names and convert them into formulas. Again, hit the pause button, work through these, and then we'll compare our results. Okay, first one, nitric acid, right? This ic acid tells us that we're talking about an oxyacid, and the ic form means that it's based on the 8 form of the anion, right? So that means we've got to start with nitrate. Right. And so we're just going to take this nitrate and convert it into an acid by adding enough hydrogens to balance out the negative charge. Nitrate has negative charge of 1, so that means we need 1 hydrogen here. So nitric acid would be HNO3. All right, our next one, Hydroiodic acid. This name has 2 parts, ic acid, but also the hydro at the beginning. That tells us that this is a binary acid in the aqueous phase, right? And the root here tells us that it's the binary acid of iodide. Iodide is -1, so if we want to form an acid for that, we have to add enough hydrogens to balance out that charge. Since iodide is -1, we have to add 1 hydrogen to that. So that's our formula for hydroiodic acid. And because it's a binary acid, we ought to include the state here to indicate that that's dissolved in water. All right, now hydrogen iodide is the same thing. Remember, for these binary acids, it depends on whether it's in the gas phase or dissolved in water. And hydrogen iodide is just the name that we give to these binary acids when they are in the gas phase. So hydrogen iodide would just be HI, just like hydroiodic acid, except that it's in the gas phase. Okay. All right, and then our last one, Hypobromis acid. Okay. This is an oxyacid, so we need to use that table, right? And the table always starts with the 8 form. So let's remember what the 8 form of the bromine oxyacid is, and that's BrO4, which is bromate, right? And this prefix and suffix, hypo and us, means that we've gone down in that table twice. So that means this acid is based, that means that this acid is based on the hypobromite ion. And if we want to make take this hypobromite ion and make an acid out of it, it's got a charge of -1, so we have to add 1 hydrogen to it. So HBrO would be the formula for Hypobromis acid. All right, so we looked at, in this little video, we looked at 2 kinds of acids. We looked at binary acids and oxyacids. And for oxyacids, we had that little table. This is important that you remember this. If you start with the ate form of some oxyanion, if you add one oxygen, and the name changes to per 8 ion. If you decrease by 1, it goes to 8 ion. And if you decrease again, then it goes to hypoite ion. And the corresponding name for these acids is per ic acid, ic acid, us acid, and hypo us acid. So this first part of the table you already memorized, I hope, when we were talking about oxyanions, and so now you just have to add another little section to that. And notice that those two are very similar. The only difference is the 8 and the ice, the 8 and the ite are replaced by ic and us. All right, great. That's it for acids, and next we will look at organic nomenclature.